Welcome to this video on the RC phase shift oscillator. We will explore its theory, design, and applications in electronics. Our journey will cover the introduction to RC phase shift oscillators, design considerations, practical applications, advantages, and limitations. Let's begin with an introduction to RC phase shift oscillators. We'll explore the definition and basic principles, including the concept of phase shift and the oscillation generation mechanism in RC circuits. This is a typical circuit diagram of an RC phase shift oscillator, featuring a three-stage phase lag network and an amplifier. Operational amplifiers are key components. Their configuration impacts circuit gain, and the feedback loop is essential for maintaining oscillation stability. Understanding RC networks is crucial. The resistor-capacitor configuration defines the oscillation frequency, which is determined by the values of R and C. The derivation of the transfer function begins by using the impedance of the capacitor and applying the voltage divider rule to simplify the expression. From the transfer function, we derive the magnitude and phase shift for a single RC stage. To satisfy the Barkhausen criterion, a three-stage RC network must provide a total phase shift of 180 degrees. This allows us to solve for the frequency-related terms. Solving for the frequency, f, we arrive at the final expression for the oscillation frequency in the ideal case without loading effects. In reality, loading effects occur due to the cascaded RC stages. This alters the impedance and modifies the denominator of the total transfer function. When incorporating loading effects, the total transfer function's denominator is adjusted from the simple cubed term to this expanded polynomial equation. For oscillation, the imaginary part of the denominator must be 0. We expand and sum the terms to identify the real and imaginary parts. Setting the imaginary part to 0 and ignoring the trivial solution, we derive the actual oscillation frequency f, incorporating loading effects. Next, let's look at the design considerations for RC phase shift oscillators. Component selection involves choosing the right resistors and capacitors for the desired frequency, and evaluating the operational amplifier's bandwidth, slew rate, and gain. Stability analysis is key. We must ensure stable oscillation by examining feedback and phase shift, and enhance noise immunity through proper grounding and shielding. Now we will explore the practical applications of these oscillators in electronics. In signal generators, RC phase shift oscillators are used for sine wave generation and are crucial in frequency modulation for communication. Audio applications include tone generators for testing equipment and generating musical instrument effects for sound design. In communication systems, they are utilized for carrier signal generation in wireless transmission and as local oscillator circuits in radio receivers. Let's review the advantages of using RC phase shift oscillators. Their simplicity of design is an advantage, requiring fewer components and offering ease of implementation for both learning and practical use. RC phase shift oscillators are cost-effective due to affordable component choices and low manufacturing costs, making them suitable for educational projects. They offer performance versatility with adjustable output frequencies and produce good waveform quality, which is beneficial for signal analysis. Finally, we must consider the disadvantages and limitations of RC phase shift oscillators. Frequency stability issues arise from temperature dependency and component aging effects, which can cause frequency drift and instability. The output signal amplitude is often limited, necessitating buffering requirements and restricting use in applications demanding higher output power. They are susceptible to harmonic distortion due to nonlinearities in amplification, which can compromise signal integrity.